Okay, yeah, so once again, thank you for the introduction. Thank you for inviting me. It's a great pleasure to be here, even though virtually. I don't have very many opportunities to actually talk and go to Slovakia. So this was really a good opportunity for me. So I was very happy that Valentino approached me last week. And it was a bit short notice, but I hope that I have prepared something which can inspire you. Um, Valentino mentioned that this is based on my 20 years of experience. Of course, I'm doing this 20 years, but I picked up some work which is kind of recent, last 5 years mostly.
Excuse me, Peter, just before you start, sorry for technical interruption.
Okay.
Can you move this, the small window on the right or on the left, on the right of your screen? Yes.
Is this
Very
better
good.
now?
Yeah, great.
Okay.
We
Good.
want to see all your slides.
Okay. Yes, so I work at Aalborg University at the Department of Computer Science. It's a young university. It was founded in 1974. Aalborg is north of Denmark, so it's relatively far away from a capital city, from Copenhagen. You can see it on the map. Also, with respect to Slovakia. So, I mean, if we would like to say how much or how long does it take, so it's about 15 to 16 hours by car. So one can actually make it also by car, but it's kind of difficult. I'm proud to be actually at Aalborg University because even though it's young university, it achieved quite a lot. So it's doing quite well. Also in comparison to other old universities, because we don't have any Nobel prizes or any old ancient Nobel prize, old ancient prizes, but still we managed to be one of the top 2% of the universities in the world in various rankings, and also recently in some specific rankings, like with respect to education and quality education, we are one of the best in the world. So, for example, MIT report from 2018 mentioned that we are actually 4th best in the world in engineering education. This year, Times Higher Education mentioned that in sustainable development goals, goal number 2, quality of education, we are actually number 1 in the world. So I'm really happy that I can contribute with my expertise and my results also to the ranking of this university. This is the outline what I have prepared for today for you. I will just shortly mention what my research is about. And then the talk is basically split into 2 parts, introduction and then some technicalities or technical part. I will not go very deep because I understand that the background of audience is relatively large. You can always dig up the details about formalizations and experiments in the papers, which are also mentioned in some slides. But I created a little bit longer introduction also because I thought that it's important to give a general picture how methodology in this area usually looks like and what we are doing, and not only me but also people within the community focusing on similar tasks. Okay, so let's just start with my research topics or themes. So I can position myself in a bit broader area, which can be labeled user-centered machine learning. So I am looking at the machine learning, but I'm also looking at the machine learning which is applied and also which is rooted in some practical tasks which support users, right? And then I'm using machine learning and data analytics to understand user preferences and user behavior in order to help a user predict something which can help user or which can help user to make decisions and so on. From technical viewpoint, I am focusing together with my colleagues on building and extending machine learning models to predict user behavior and personalization. And recently, I have mostly focused on a couple of algorithms or models, and they are collective matrix factorization, similarity computation, especially in vector spaces, random walk models, neural network or deep learning based models, and also in the past, a few years ago, some topic analysis models. But let me start by introducing the whole area from practical viewpoint, right? So we are, I mean, digitization, this is kind of a modern word, which is driving even all funding agency in strategic research. Digitization means, it started actually a long time ago when first applications started to pop up. Shopping online is there for a number of years already. We all have tried that. Now in pandemics, actually, these companies and these applications, they boom, they hire new people because people simply don't go out. They can't go out. So they shop online and they get them, they get the goods delivered directly to homes. Typically here, for users, it's important to recommend something which is interesting for them because they don't want to lose their time. They want to quickly shop and they want to get their goods as fast as possible home. But from shops, this is also an important area because they can plan accordingly what they should have on their warehouses, how they should optimize their logistics, and so on. So this is one area where understanding user behavior and predicting what the user will buy has a huge impact, and where this is also important for businesses and not only for the users. Entertainment media, it's another area. We all watch Netflix, or HBO, or there are a number of streaming services. We also stream music. We listen to music even when we are in the car or well, at home with family. In here again, for companies, it's important to understand the user behavior because they need to have a content which users will keep streaming, right? And if there is not enough of such content, or the recommendations of such content is not appropriate to what these users would like to have, users will start dropping from the subscriptions, right? So this, I mean, well, this happened to me, right? So I just dropped my Netflix subscription and I moved to another streaming service. So from the company business perspective, it's important because they want to keep their customers and subscriptions because this is their money. And for users, of course, you don't want to spend like an hour of clicking to find your movie, or click and skip songs on your mobile phone when they are recommended, right? So again, understanding user behavior is important, and predicting what the user will watch or listen to is important because it's relevant directly to the business of these companies. Obviously, social media, I mean, now this is kind of with mixed feelings, of course, because especially in pandemics, we have seen a lot of hoax around, and social media have been misused in many events or many directions. But still, I mean, Facebook lives from the advertisements, so at least the recommendations of advertisements is important. Also, I mean, trust towards such social media is important, so recommending trustworthy and not so hoax information is also important for them. But there we see that there is still a way to go to actually achieve something which works a little bit better. But I mean, this is an area where these user analysis, understanding user behavior, and also understanding how friends come into this picture is also important. Of course, we all Google. Well, some people Bing, some people Google. Google's main income comes from advertisements. Recommendations of advertisements is important for them. So of course, understanding what user will search for and click on is also important for them. So in this case, I don't have to talk even too much that, and you will immediately buy this argument. This is important for them. Even though here we have this mixed experience as well, that we sometimes get not very relevant advertisements. But you can see that for Google, this is sufficient, and they still earn a lot of money on this. Similarly, I mean, another area of online user activities are blogs and encyclopedias, where also to a certain extent recommending from blogs and from encyclopedias is important if users want to optimize their time spent on the task. In here, I mean, these are usually not commercial organizations, even though WordPress is, so some sort of advertisements is important for them too. But there are many more, and it's actually growing significantly. I mean, now we can see we are streaming online our lectures. I get the full report of what users of our platform clicked on and what they spent on, what they looked at, and so on in my lectures and in my exercises when I'm doing it online, which can be used for optimizing even our teaching. But there are also, I mean, other activities and new innovations which are coming into the place. And there is a lot of content out there. So from user perspective, it's always important that we do not lose so much time inside the hyperspace on an overload of information. So this is basically the practical picture. So from all of these, we can take that users actually leave a trail of their behavior in each of these systems, right? And these clicks or trails or activities, they are basically signals of the user preferences, interests, and needs. And it's a rich signal, right? So, I mean, why don't we, I mean, and not only me, but many other people have recognized that. And obviously there is a huge research and a huge community behind this. So people are looking at these signals and developing new models. These companies actually have their research departments where people are spending a lot of time on applied research, especially on understanding these signals and improving the businesses, actually. So it's not only an academic research, it's also industrial research. And I'm quite excited about it. And I hope some of you will also take that excitement and then see whether you can do something about this. But let's just look also at some examples. So this is one of the sites where users can express their opinion about restaurants or businesses, right? And they can write reviews, they can rate, and they have their friends. So we can actually find even friends' opinion and compare what people have thought about specific places and how their preferences can differ, right? And we can extract it from some kind of a raw data, right? So we have the ratings, as I mentioned, we have the text. We can see in the highlighted text that this specific person commented on some English, commented on some kind of food, and commented on some price, right? So these are kind of, you can call them features, which you can extract from this text, and that you can use them for prediction or for understanding what user is really interested, right? Similarly on Twitter, right? So there is a stream of activities, stream of tweets, which you can read or you can forward, or you follow friends. You can follow friends' tweets as well. So from Twitter, we can actually, similarly in the previous picture, we can understand from what users have written, what their interest might be. We can understand from friends the user follows whether there are some additional similarities in interests and see whether we could extract something from it. So I have just listed here on the right side of my slide what could be features which could be taken into account for understanding of a user behavior, but also for predicting whether specific tweet is of an importance or not, right? So how does the typical pipeline usually look like? So I mentioned that we start with some raw data which we can get from some sites or from some applications or from some logs, right? Because in Amazon, for example, case or in a Google case, this is basically a query log, what users have submitted to a search engine or what users have bought. So we have the raw data, which we need to somehow pre-process first, right? So I mentioned also on the previous examples that we try to extract some kind of features which could be relevant for understanding the behavior or for predicting what user may like or may not like, right? So, and in both cases, so in user case, we try to model features which are relevant for a user profile. And on the other side, we also need to model or we need to understand features which are relevant for in general sense personalization target, but you can replace personalization target with a specific item on a Amazon shop, or you can replace that with a movie which you are recommending on a Netflix, or it's a song or a playlist which you are recommending on Spotify, and so on, right? So I just wanted to basically provide a general picture for any kind of recommendation or any kind of target personalization. This is typically quite high dimensional. You can look at it so that if you extract something from text, the dimensionality of features of a text can be quite high. So for example, English has around half million words in the dictionary, right? So if we would consider the whole English vocabulary, we would have 500,000 dimensions of a vector if you want to have one hot vector representation, right? So you have to see it from that perspective, that some features may be for some values, but some features can be some binary attributes, and they can be expanded to quite a lot of features. So that's why this is quite high dimensional. High dimensional is not good for computing, right? So it's very difficult to computationally difficult to get some predictions on time, especially when we have a lot of items and a lot of users. So if to get some practical approach, we need to have some kind of a model on top of it and then reduce the dimensionality. So we map usually these features into some vector space, which is typically lower dimensional, where we have on one side user representation and on another side target representation. And here again, it's either advertisement, it's a news coming into your Facebook, it's a recommendation of a product, or some other target which one would like to get recommended or get help with. And then once we have it mapped to this lower dimensional space, then we believe that we can get the computation a little bit easier or easily done. Here, then we basically just do some matching. Typically, this is very often a dot product between some vectors which are representing a user and a item, and then based on the matching and some kind of a score, one can typically order the recommendations and output them to the users, but the process and the user interface can look very differently, right? So I'm not going to talk too much about user interfaces here. My focus is on computational part, and typically we output either some kind of a number for a specific item, or we kind of output a list which orders the choices for particular user. Right. So if I go back to my research, so in the beginning I have mentioned these companies. I use some benchmark data sets which are also based on these companies, or these companies have provided, and I focus there on some recommender systems. I have also focused on some text extraction and summarization for social media. And I was also focusing in the past on some understanding spread of influence in social networks, because this is especially relevant for marketing and how to spread information about specific items in the social network, where to start and so on. But I'll just reduce the rest of my talk to few of these works. So I will focus on recommendation systems, and then I'll also present something about summarizing trending topics on social media. Right. So now I will move on to a little bit more technical, the technical part of my talk, and I would like here to emphasize two take-home messages. Right. So preferences and user behavior are contextual, and recommendations should be as well. So in here, I basically argue, and we have kind of showed that in our experiments that it is better consider some context of a user activity, because then we get better recommendations taking into account that context. And another take-home message is that we need to consider not only positive but also negative signals in preferences. Or in other words, models based on both positive and negative preferences perform better than just those which are taking into account only positive signals. So let's just start with the first one. I will now look into two approaches for contextual recommendations. This work was done together with my former PhD student who has graduated in 2019. He's now actually working for some kind of a chain of supermarkets in Denmark, where his task is actually to develop recommendation systems for them. So directly his PhD opened him for an industrial career. So this is also an example that one does not really have to stay in academia even when he or she has a PhD. But let me just go to the work. So the motivation for this is, like, if you look at the movies, we watch the movies usually according to some kind of a context, right? So, and the context you can imagine as some kind of a time interval or a time point, or you can imagine it as some social context that you, for example, watch it with family or with some friends and so on. And typically, when you watch a movie with a friend or with some friends, this will be kind of different, unless it is somewhat popular movie, right? But it will be somewhat different than if you watch it alone. Similarly, I mean, we tend to watch some other movies during winter and some other movies during summer, right? So I mean, here we can kind of see that this makes somehow sense, that if we consider these kind of contexts, we will be probably able to get something out of it. So how do we actually represent, right, these data? So I mentioned that one of the methods which I focus on is a matrix factorization. So matrix factorization, in a practical sense, I mean, it's a mathematical method, but for practical applications, we can say that by matrix factorization, we are trying to capture some latent variables which can describe both items of interest, but also a user profile, right? If we look at the raw data, we typically record user activities in some kind of a user item matrix. And in this case, this is XU matrix, where we record ratings which the users have placed for particular items, such as movies. Then another matrix here we can see records a binary value about some content, and the content here you can imagine as genres for a movie, right? So, but it can be more, but I mean, just to simplify it a little bit, let's just say these are genres. So if you have a movie, or if you have a user who has liked let's say some genres, then he will have one in in that cell for particular genre. And then that's the similar for context. Again, I have exemplified the context on the previous slide. So it could be some kind of a time interval, time of a day, or it could be a season, right? And then we have a binary representation of raw data for particular context where users have entered some kind of preference. So once we have these raw data in matrices, we have an evidence of what users have liked. Now, these matrices or this data is quite sparse, right? So there are lots of zeros. For zeros, we can't say much. So what we want to get is we want to actually fill in those zeros at the end with some predictions. And of course, these methods, they usually take into account what users have expressed. So those values which are non-zero values, and then they take them and then use them as patterns and then try to kind of fill based on those patterns the rest of the matrices, right? So and then so in practice, we are trying to find some kind of a split of the matrix into some factorized matrices, which at the end, when we multiply them back together, then the difference between the evidence in the data and the multiplied predicted value is as small as possible, right? And this multiplication, once we have learned these factorized matrices, multiplication back fills in the zeros and then gives us the predictions also for the unknowns. In here, we have created a method where we do this matrix factorization jointly. So you can see in this minimization function that we have a matrix W in each term, right? So we have it in the first term together with XU and HU. We have it also together with XA and HA. And we have it also together with XC and HC. So this W is actually a common shared space, which is used to put all these things together. So if we, for example, get some information in a real application just from, let's say, contextual or content attributes, and we don't have the ratings, we can also transform through this shared space back and predict still the user preference even for an unknown item. So we do some kind of an optimization. In here, we also have proposed and validated some kind of a hybrid learning model. In previous work, the iterative updates for learning these matrices, they have been uniformly updated by update rules which are coming from a gradient descent method or from gradients of the optimization function. We have found out that this is sometimes relatively slow, even when we use a stochastic version of that. So we have experimented with some other methods, such as Barzilay-Borwein, where we have the adaptive learning step. We have actually found out that it works the best if we combine them. So for the shared space, the learning step is not adaptive, so we have traditional multiplicative update rules, while for the partial matrices, we have an adaptive process, and we kind of calculate how much we would like to jump towards the objective in the optimization. Okay, so if we look at this, so this is kind of still linear model, right? So this is trying to learn some linear dependencies between users and items, users and context, and users and content. We also know from other works, from other colleagues, that sometimes there is no clear cut in these relationships. So there are sometimes nonlinear dependencies, and these matrix factorization methods, they are not very good at capturing those. So we have kind of took the idea of joint matrix factorization and tried to propose a method which also captures these nonlinear dependencies. And we have proposed a method which is based on a neural model. and specifically convolutions. So typically this has then several steps. First, we are kind of embedding the raw data into some space, and then once we have it in the space, we could apply convolutions and filters over this data to find out how users and items relate to each other, and how users and context and items relate to each other, to find also these hidden and nonlinear dependencies. These filters, they are also learned. So we are actually not constructing them, we are learning them as part of the process. And of course, the details you can find in this paper, but let's just now look at some results. So typically when we look at the results, well, we need to fix the task. So in this case, we basically said we are predicting a ordered list of items. So we are outputting a list, and we try to measure how this list perform, right? So what is good, how good the list is. And there are various measures how one can assess this. We are typically running it in a so-called k-fold cross-validation. So basically we split the data into 5 to 10 folds, and then we take out one fold and then do the training or optimization on the rest, and then test it against that hold which we have taken out. In that and then we do it 5 to 10 times depending on how many folds do we have, and then we average out the results in metric which we choose. In this case, we report a metric which is called normalized discounted cumulative gain. In short, this is basically a metric which tries to find out how good list is also with regard to the position of the items which you should have recommended. So it penalizes items which are too low on the list, and it gives more gain to items which are on top of the list. And then this is a measure which outputs a value between 0 and 1. On the picture, we can see that there are differences on different data sets. So columns are actually different data sets which we have tried our method on. And then the difference is significantly larger between Frappe and the rest, right? We can see that here we achieved 0.8, which is a relatively high number. It's relatively close to 1, while on the other data sets, it's rather on the opposite side. The reason for this is that the data set Frappe has a rich context. So it has all the social context, time of the day, even a mood, right? So we could actually use a lot of the signal from the context to actually find out better recommendations. And we can actually see that on the value, right? And we can also see, like the last row, this is our method in comparison to some baseline, state-of-the-art baselines, some matrix factorization baselines, but also some other baselines. I'm not going to spend more time on this, and but we can see here that we outperformed the performance in comparison to the other methods. Now we have also tested those rich context data sets. They are relatively small because it is difficult to get. Very often the data sets only contains the timestamp, right? So we have transformed, we have taken those data sets, so about movies, about restaurants, and about pins, and we have transformed the timestamp into some kind of a context, time of the day, right? And then we use that and then try to see how we perform in comparison to other methods. And here this was the second experiment where we also consider not only linear methods, but also nonlinear methods like neural network methods as baselines. And here we can see actually that the neural methods almost always outperform the nonlinear methods. We can also see that our convolutional neural network is adding to it, and then so that's the last row. So we are again outperforming the other methods. Here we can see that we use two measures. We use the same measure as on the previous picture, which is normalized discounted cumulative gain, NDCG. We use also HR. At N, HR is not taking into account position. It normalizes across users rather than across all the items. So there is slight difference between these two measures, but it seems that they are, in our case, correlated, and we are getting better performance on both measures. All right, so from this work, the contributions were from user behavior modeling perspective, preferences learned in the context contributed to better performance of recommenders. We have seen that clearly even on the data set with a rich context where the value was suddenly boosted to a very high NDCG value. We also have seen on the results that there are also quite some nonlinear interactions in all views, items, users, and contexts, because not these neural network models, they performed all of them actually better in our experiments. And so capturing them helps to improve these recommendations. From the technical contribution standpoint, we extended the joint collective factorization with additional contextual data and model embedded in hidden context metrics. We have proposed hybrid optimization with update rules and Barzilai-Borwein methods, which converges actually faster. I have not shown these, but you can find it in the papers, but it is really performing faster, especially on the larger data sets. And then we have proposed the convolutional neural network-based model for context-aware recommendations. We have now also moved a little bit further. In a recent work, we have asked ourselves, is this matrix representation actually the best we can achieve? And we have kind of thought that if we move to more graph-based representation and consider models based more on link prediction on the graphs instead of playing with matrices, we thought that this could actually contribute to some precisions, but this is kind of this is recent work, so we are not finished with that. We are continuing, but let's just kind of introduce it. Quite many people are looking into this, so if someone wants to start some research into this area, this is the area which is now, right? So this is something you can just take on and then do something in here. So we call it knowledge graph. It's a term which basically describes some kind of a data model which contains information about items and their related attributes. Here is an example. So if you want to record an information which we had before on matrices about what users likes, and with side information, so we can get a graph like this, but of course it's usually larger. So this is really just for an example. So user likes, let's say, Cloud Atlas, which is a movie, which is based on Cloud Atlas, which is a book, with a genre, which is a science fiction, and then it stars Tom Hanks as an actor, and it has directors and other information which I have not even pictured here on this picture. So here we have only one direct explicit expression of interest on the movie directly. We have further extended this and said the users are allowed to actually give likes also on side information or on entities or whatever you want to call it. So basically this means that we can actually express our preferences on books, genres, actors, directors, or what have you in this data. And we want to kind of predict whether some other users will like it based on this information and the history of that user, right? We have also developed an application, and you can actually try it yourself because we are actually collecting the data from users about these preferences, and we are putting this data back to the community as an open data set. So the MindReader is an application where through a game, we are actually eliciting both negative and positive preferences on movies. And we try to use the data set then for experimenting with the methods. I'm not going to the technical details of those methods. I'm just showing some results here. Here you can see again both metrics I have already mentioned. So hit rate, HR, and normalized discounted cumulative gain, or here we just abbreviate it as DCG. And just to make sense of this table, if we consider all movies column, this is about ratings only expressed on the movies. If we take all entities column, then this is about ratings also on entities. And then these third 3/4 or half or 1/4 of values, these are basically for different combinations of ratings from movies and entities. But we don't have to look at that. You can actually get that from the paper. But let's just look at the first two columns. We can see that there is a difference between performance of state-of-the-art methods. So the bottom part of the table are methods which are based on graph embeddings into some vector spaces. And then the PPR methods are basically PageRank or random walk methods. Then there is a matrix factorization, which is MF, but also BPR is matrix factorization method. And then item KNN, this is a KNN-based classification method. So we can see that if we only consider on our dataset, our created dataset or elicit dataset through the mind reader, we can see that actually top popular recommendation, which just outputs top popular movies, performs the best. But if we consider on our dataset also the ratings on entities, we can see that random walk-based method actually performs better. What was a bit disappointing for us was that current state-of-the-art graph embedding methods are not performing close to that good as the other older methods. So you can see here, I mean, there is a lot of work going on in machine learning communities on these graph embedding methods, but they are not yet at the level where we would want to have them in practice. So again, some pointer that this is something where people can do research in and can get some results. And if they are lucky and if they are clever enough, they can actually publish on top conferences, because this is recent again. Okay, I'm not sure I would like to go further than this because, well, I had another part about social networks, but I think we are running a little bit out of time, and I would like to also give some space for a discussion. But let me just move through this one and go to some closing, and then we can have the discussion. So we saw on those methods that which I have presented, that contextual information and signal actually have given a boost in performance. We have also seen, I mean, I have not talked too much about the negative preferences. I have just mentioned that we actually elicit them. We elicit them through mind reader, so we have them in the data. So we consider them in those methods which we actually are running. Also, this negative preference part was also a strong part of the technical method for text summarization, which I have just skipped. But still, I mean, the message is there. So negative preferences are also important, or negative feelings are also important when taking into account in these machine learning models. Now, I have presented the work in some applications, but there are also other applications which are interesting and important also for the future, right? So intelligent and green transport is one of the United Nations Sustainable Development Goals. So, and there actually recommendations of roads, recommendations of multimodal transport, where to shift, and then taking also into account the CO2 emissions and other things. This is quite interesting, and this is quite important also for the whole world, right? Adaptive human-robot collaboration, this is kind of practical for the future. So robot, I mean, we want to have environments in industry where robots work on some high-level tasks together with humans, right? Because we cannot replace humans completely. But still, practically, this is not yet completely possible because robots are not able to actually go around and not crash to human, right? So we want to have an environment where these robots are actually able to recognize a risk of running into some man or cutting a hand or something like this, depending on the task. So the robot needs to kind of learn, well, it's a preference of a task, right? So, and it's a preference for not harming, but still going towards the goal of the task. So this is kind of a long shot yet, but there the user modeling and preference learning is quite relevant for robots, right? In personalized healthcare, recommendation of activities and practices, so proactive way of looking at health. This is where recommendations are relevant because they prolong life, right? And then they also decrease the need for medicine. And then personalized smart industry, at least more effective knowledge sharing is interesting, but also this is related to adaptive human-robot collaboration, where this preference learning has also quite, in my opinion, quite a value. And then for promising methods, I have listed some of them here, which I am interested in. There are probably more. One-shot, few-shot learning. So, you know, I mean, we don't have always the data, so we want to learn on the data we have, but we want to kind of transfer that to area where we don't have data, and either we do that through transfer learning per se, or we do it through some kind of a few-shot, one-shot learning. Again, you can Google it, you can find papers about it. These are interesting, these are hot. Reinforcement learning is hot for companies as well, also for the cars per se, so not only user preference learning, but also learning in autonomous cars or other contexts. And then, of course, imbalance in the data. Real life data is imbalance. We have a lot of positive signals, not a lot of negative signals, or other way around sometimes, and how to deal with that. This is also interesting to work on. So I guess this is it from my side.